Okay, in this video, we're going to look at creating and solving exponential equations. So remember from our previous lesson, we talked about exponential and growth and exponential decay. So keep in mind an exponential growth model looks something along these lines where you have an initial value and you have, in this particular case, we're looking at rates. And the 1 stands for you're taking 100% of your total and then you're going to increase it by whatever percentage rate they ask. T will be our time. Exponential decay, when we're looking at that model, again, we start with our initial amount and then we take 100% of our total and we subtract a certain rate. So that's why you'll notice that that one's 1 minus r. Notice that it's also to the t, which is time. Okay, so keep in mind the growth factor, the growth or decay factor is the b value, and that's the ratio between the 2 consecutive y values. Okay, so there's a growth and decay factor, and then there's a growth and decay rate. So r is the rate, whereas b is the growth and decay factor. So let's take a look at how one of these might work. So here's a kind of a basic one. So we are going to use this exponential model where we have an initial amount, and then we have our growth factor, and then we have our x in the exponent, which in this case is going to be time. So we have the initial number of bacteria in a culture is 1200, and the culture is doubling every day. So we're going to write an exponential function to model this. And we can do this a couple ways. If I follow this basic exponential model, my initial amount of bacteria was 1200 and it was doubling every day. So one of the ways I could work this out is I'm going to take 100% of my total and I'm going to add to that another 100% of my total. If you notice when you do this, that's going to give us a 2 in there to the x power. So doubling does mean a 2. So you're doubling it each day. That's implying a 2. One way to tie it back, though, to those growth and decay factors that we just talked about a second ago was to think of it as 100% of your total plus another 100%. Okay, so how many bacteria would there be in 3 days? So now we can use our model. So I can take this model, and days is the x. Okay. So I can type in 3 days up there and grab your calculator or Desmos, whatever you're using, and we can say the number of bacteria is about 9,600 after 3 days. Okay, so how long until there are 1,000,000 bacteria? Well, one way to do this is to use that table feature in Desmos. Okay, so if you go over to Desmos, you can type in the table, and we can kind of see in here, you know, we're getting very close to 1,000,000, 9.5, 9.7. So I would say probably around 9.7 gets us pretty close to that 1,000,000 bacteria. So we're going to learn some other ways to do this in future units, but for right now, what we can do is we can look at that table and do some estimating from our table. Okay, so let's try this one. You decide to start a new career raising bunnies. You buy a bunny farm that has 10 bunnies. As part of the sale, you were told to expect the bunny population to increase by 80% per year. Okay, so we will write an exponential model. So notice we're talking about increasing. So that tells me we're going to do something with exponential growth. So my basic model, again, is AB to the x. My initial amount was 10 bunnies. And if you think about it, we're taking 100% of our total and we're increasing it by 80%. So I'm going to add 0.8 to the x. Okay, and x is my time. Now I can also simplify that as 1.8 to the x. Okay, but I just want you to understand where that 1's coming from when you do this, because I think one of the misconception is you see the 80% and you want to put 0.8. Well, you got to keep in mind you're taking 100% of the total bunnies and you're increasing that by 80%. So it's 100% plus the 80%. So just be mindful of that. Okay, how many bunnies will we have in 5 years? This is where we can use our model. And we can substitute in our 5 and grab your calculator or Desmos, and we can see it's about 188 bunnies. Okay, so in 5 years, we can have about 188. And then the person who sold you the bunny farm predicted you would have 1,000 bunnies in 10 years. Were they correct? Okay, so if I want to check this out, let's type in for 10 years. Okay, so if we did this for 10 years and we do those calculations, we can see we get about 3,570 bunnies. So yeah, you're going to have way more than 1,000 bunnies in 10 years. And my mathematical support and reasoning is my equation here. Okay, let's try another one. So Tanner buys a new truck and plans to finance it for 5 years. Trucks depreciate on average 20% per year. So if you're not real familiar, depreciate means it's decreasing in value. Okay, so this would be more of an example of exponential decay. So we're going to create an exponential model relating the time t in years to the value of the truck f of t in dollars. Okay, so again, it's still that main basic equation that y equals ab to the x. But this time they want us to kind of use their variables. So that y is going to be the f of t. That's just function notation. The initial value of the truck we can see over here is 33,495. My growth factor, it's 100% of the value of the truck, but this time we're decreasing 20% per year. So I'm going to put minus 0.2, and then I'm just using the variables they said. They said put t for time. I could also simplify this to be 0.8 to the t. Okay? How much will his truck be worth when he pays it off? Well, it told us it was going to take 5 years to finance that. That means he's going to make payments for 5 years and then he'll own it. So if I want to figure out for 5 years, I could substitute in f of 5 and do that to the 5th power. And again, grab your handy calculator or Desmos calculator, and we can see in 5 years when he pays this $33,000 truck off, his truck will be worth about $10,000, almost $11,000. Okay, so we had a couple exponential growths, and that was an exponential decay. Okay, so let's create a table and graph the values of that truck over the next 10 years. Okay, so we're going to see what this looks like. You should have in your head that it's going to be somewhat of an exponential decay model. So when you make your table of values, you could do this in Desmos. What I did was, over 10 years, it doesn't necessarily mean you have to graph 10 points, but we just want to do something over 10 years. So if you notice what I did in the table, I counted by 2s. So I don't, it doesn't really matter what you go by, but I would try to get about 4 or 5 points when I'm graphing these things. When you make your graph, time will be on the x-axis. So we can put down here, this is time in years. And then over on the y-axis, this is going to be the value of the truck in thousands. And so I want to draw your attention to how I did the axis here. So again, you can pick whatever scale you want, but notice these are nice and evenly spaced. I counted by 4s on the years, and then I counted by 3s going up the y-axis. Now this 3 here actually means $3,000 because I've titled that in my label that those were in thousands. Okay, so again, you can be very flexible on what you're going to make your scale, but I noticed my truck has to go to $33,495. So I knew I had to get that y-axis somehow evenly spaced. So I just counted by 3s. I think I played around with maybe doing 4s or 5s, but I figured I could get 3s to fit up there, and just some things to look for as you're doing your tables and you're graphing them. Okay, so if I want to find the values of each of these, I can substitute in my x values. I could substitute in 0, I could substitute in 2, I could substitute in the 4, and notice the values of these trucks, they're decreasing. Okay, no, they're not decreasing by the same amount every time, but they are decreasing in that common ratio of 20%. Okay, so I'm going to go through and graph these. And so 0, 33,495, I'm going to estimate is about right there. That is our y-axis, or our y-intercept, I'm sorry. And so that means, so this guy here, he's our y-intercept. And that means that's the initial value of the truck. Okay, so that y-intercept is always your initial amount. Okay, so then I'm going to go over here. After 2 years, I'm worth about 21,000, a little more than 21,000, so maybe estimate it there. And 4 years, we're a little more than 13, so maybe something around almost 14,000 for that one. Year 6, I'm around 8,000. Almost 9,000, pretty close there. And year 8, we're at almost to 6,000. And year 10 will be here a little past this. So I can start to see that this is coming down and it's starting to make that curve, okay? Now that will keep decreasing. It will never ever be worth $0, so it's never going to cross that x-axis. So we can show that end behavior by putting a little arrow on it, and I have the end behavior up here at the top with the point. So this is an example of exponential decay. Okay, and we can see that, and it makes sense because the truck was depreciating. So that word depreciating means that it is decreasing in value. So again, take note of that y-intercept and that end behavior. That end behavior is going to continue going closer and closer to that y or that x-axis, but it won't actually touch it, which means your truck will actually never be worth $0. Okay, now an extension of this, when will the truck be worth 5,000? Again, let's head on over to Desmos and make a little table. So I can kind of start seeing here my table. I'm getting a little closer to 5,000. So if you notice, I'm between 8.5 and 8.6 years is when I would be around $5,000. So I would say around 8.5 years would be a good estimate. Okay. So at this point, we're just kind of doing some estimations by looking at our tables. Again, like I said, in the future unit, you will learn how to do that by hand. Okay, so I think that's it for this little lesson. So hopefully you kind of learned a little bit about the exponential models, and you are good to go now to go and try your practice.